What is going on, everyone? Welcome back to another video in my EE Fundamentals series. Basically where I go over any sort of engineering concepts that I think are relevant to learning how to effectively design circuits and design PCBs and things like that. So today's topic of discussion is going to be EMI, aka electromagnetic interference. I'm just going to give a quick overview of what we'll be talking about in this video. So kind of be talking about what is EMI, why does it matter, some compliance standards that you need to be aware of, types of emissions. We're going to look at some example tests, some example test setups. Finally, how do we mitigate EMI, and learn about some of the technicals related to EMI mitigation. And finally, we'll look at an example of an EMI filter. Alrighty, so jumping right into it. What is EMI? EMI stands for electromagnetic interference. I'm sure a lot of people already know that. Some good examples I think you might have encountered in your everyday life are speaker hum. So say you have a speaker that is perfectly quiet, it's not playing any like audio at all. Like say you're not watching this wonderful YouTube video, walk up to it and put your ear very close to it. You might hear like a hum or like some crackle or like a white noisy sound. Especially if you have like big like studio monitor type speakers, like some like big old Yamahas or something like that. Then you'll probably hear some background like hum or crackle or something like that. The same thing goes for if you've ever recorded your own voice with some type of voice recording software that doesn't have automatic filtering on it. So a good example is Audacity. If you ever record your voice on Audacity, when you hear the first playback, you're like, wow, it's so noisy. Like, how do I, like, where did that even come from, right? That's from EMI being picked up by not your microphone itself, but the microphone cable is acting like a receiving antenna, much like a radio would, or like your satellite dish antenna. If you ever, I know those are archaic example because everyone uses the internet now, but and sort of Bluetooth, right? Those are used antennas as well, or Wi-Fi uses an antenna. So that's kind of what your microphone cable is acting as, an antenna receiving a bunch of EMI. So the underlying physical phenomena that sort of create EMI, we've actually already covered it before in a previous EE Fundamentals video. So I have a note here, recall previous videos about Faraday's law and electromagnetic inductance. Basically what it is here is it's an unintended consequence of Faraday's law, and electromagnetic inductance is basically what is causing EMI. It's unwanted electromagnetic inductance. So it's unwanted changing magnetic fields, fluctuating, permeating throughout the ether that is being picked up by our sweet sensitive electronics. And so that's just something we have to deal with because Faraday's law is great and we can harness that physical phenomenon, do a lot of amazing things, but there's just there's give and take here. It's kind of like gravity. You want to be able to jump really high, but gravity keeps you on the earth. So you gotta take it for what you gotta take what you can get, I guess. So why does EMI matter? Well, I guess I should quickly go back to note that EMI is actually being produced by the very electronics that we use, right? So your cell phone is producing EMI as well as being affected by it. So as I said, it's a double-edged sword here. And the reason why it matters is because EMI that goes unchecked can really rustle some jimmies. When I say really rustle some jimmies, I mean we're talking about everything from just malfunctioning electronic devices like your phone or your computer or something like that, all the way down to your grandfather's pacemaker stops working and he dies because of EMI, right? It could be because of EMI, I mean. So there's some pretty dire consequences to this, and there's some pretty, we can call them mundane, right, or annoying ones. But nevertheless, it's still really important for, in society, think about all the electronic devices and electronic equipment that surround us, that the EMI is properly mitigated in all those devices so they can, live harmoniously and live and thrive in the same environment. So that's kind of why, EMI matters in a nutshell. moving on, we have there are several standards, right? Talking about when we're talking about mitigating EMI, there are standards where people, different countries have developed to figure out, well, how do you know if EMI is properly mitigated? How much EMI is too much EMI? And the answer to that can be found if you're in America. You just Google FCC Part 15B is one of the compliance standards you'll have to deal with. Or if you're in Europe, CISPR 22 or EN 55022 are some common ones. And there's, depending on what industry you're in, if you're in there's personal electronics, industrial electronics, there's like medical grade, military grade, stuff like that. So this is more of a just know your industry, right, type of thing. But at the end of the day, they're all going to result in you having to run a test and having to, you'll see what this basically is some type of it's like a threshold, right, measured in decibels. That just measures how loud your signal is. So like I said, at the end of the day, you're gonna have to be just trying to get your EMI below a certain threshold, right, which is marked by these lines right here. So we see here we have FCC Part 15 Class A, right? So what happens is you put your device and you just test it and you measure the EMI that is radiating off of it, and as well as there's conducted EMI, which we'll talk about in a second. But you just measure it and you just have to make sure that the quote unquote the loudness of the signal or the volume in decibels is below the required threshold for your industry, for your compliance standard, right? You're trying to meet class 15A, then it has to be below this line, right? So hopefully that's self-explanatory now, or I've thoroughly explained it. So what I just talked about, what I said radiated and conducted. So there are two types of EMI emissions, right? You have, like I said, radiated emissions or conducted emissions. So radiated emissions are emissions that I have here travels through the ether. I mean, as you know, EMI doesn't actually travel through the air, but for all intents and purposes, it's the wireless part of EMI, right? It's what causes Bluetooth to work, right? It's like you have a whole bunch of Bluetooth signals bouncing around off each other. They could be interfering with, other types of signals or other electronics on your phone, right? So we need to, make sure that your phone, well, maybe wants to give off Bluetooth signals, it's not giving off other wireless signals, right? So that's just measured, wirelessly. The other type of emission that you need to be familiar with is what is known as conducted emissions. The conducted emissions are kind of what I talked about when you had the microphone picking up noise. That is the emissions that make their way actually onto your electronic, like copper traces or wires or any type of conductive material can be measured. Like I said, conducted emissions, right? Measured on any sort of conductive material. The most common example for conducted emissions, and we'll talk about the test setup in a minute, is that if you say you have a electronic device plugged into the wall, as a lot of people do, if it's not battery powered, right? Conducted emissions actually travel upstream, so to speak, right? They travel through that line cord and into the wall, and they travel all the way back to the power lines, right? And say you have 50 houses all running on the same power line. They're all their emissions, all their conducted emissions are just going to sum up, and it's just going to cause tons and tons of problems. So they're also that's how you came up with conducted emissions tests. So again, looking at this chart, radiated conducted emissions, the test will look very similar. You might have a different bar. So like, for example, class 15A might have a red bar up here for radiated emissions, and then the conducted emissions could be somewhere way down here, right? And the test setup is a little bit different. But just know at the end of the day, you're just trying to get your emissions, reading, your measurement, your emissions volume below the threshold, in both cases, in radiated and conducted emissions. So here, right, we have an example of a test. So this blue line will be a recording or a measurement of the EMI that your device under test is actually giving off. So this could be, in this example, this could be radiated or conducted. I'm not sure which. But this is what it'll look like. You have some little squiggly lines going across, and you kind of see across this frequency spectrum the levels that the levels of EMI that your device gives off, right? And so in this case, this one clearly passes because its levels are well below our threshold line. And like I said, you would have 2 separate tests per device, one for radiated, one for conducted, and you pass the same way in both cases, right? If it's below the required threshold. So moving on, so like I said, there's a conducted test and a radiated test. So we're kind of looking at some very crude diagrams I just pulled off the internet, kind of show like here's how a radiated test is done, here's how a conducted test is done. So let's say this is like your little piece of electronic equipment. This is your PCB that you designed. This is a cell phone. This is, whatever, a tablet, a computer. You put it in a little chamber, and then you have this antenna, right? Remember how we talked about a Bluetooth antenna, a receiver, right? So this thing, the EUT, I think it's like electronics under test or something. It doesn't matter. It's your little device is playing the role of the transmitter, and then this antenna is playing the role of receiver, right? Or the antenna is playing the role of the antenna, I should say. And then you have a receiver here that is just measuring the data, right? So we're basically just measuring how much energy this thing is putting off. We're measuring the volume of the signal at a particular distance, and that's how you get this curve right here. Is it's being picked up by this red thing, and this red thing is saying, okay, well, at this frequency range, here's the levels, right? Same exact concept. That's exactly what's going on. And then for conducted, you have, so this probably looks a little bit more complicated, but basically what you think about is, okay, let's say you're going to plug something into the wall. So you have your wall outlet, you have your device that plugs into it. So what this little listen box, what happens to it, it gets plugged in between the 2 devices, right? So you route your line cord through it. I say when you route your line cord through it, you plug your line cord into this little box, and that little box has its own line cord that gets plugged into the wall, right? And so then you do the same exact type of measurement. And so this thing acts as the quote unquote antenna, the little thing that records, that captures and records the data, and then that gets output on this little spectrum analyzer EMI receiver right here. So it looks like that. So again, the test is going to end up looking exactly like this. The levels will be very different, probably. But again, you're going to get some little squiggly lines, and you're going to have some threshold lines that you got to make sure you're under. And that's like EMI testing in a nutshell right there. If you're curious, you could probably Google something you might want to check out is an EMI chamber, because there's like a little special chamber that all this stuff takes place in. So you don't have, it's just like, being, doing good science, right? You want to try to mitigate any confounding variables. And so that's why you do it in a chamber, because it blocks out all other signals from the outside. Alrighty, so moving on, the next important topic is going to be, so how do we mitigate EMI? So we just spent all this time talking about how big of a deal it is and how we measure it. So what happens if your device is failing? What do you do? So the best place, the cheapest place to deal with EMI is during the design phase, right? There are solutions that you can implement after the fact, but the later you wait, it just gets really expensive, right? And a lot of times it could just ruin your design. Like say you had to put some type of metal shield over your device after you've already spent all this time designing and stuff, that could just totally wreck your project, right? So, like I said, it's really important to understand some of the critical design, fundamentals that create EMI, right? So one of those is designing an EMI filter. So this is just going to be a collection of components that we'll go over in a second that help mitigate EMI, and this helps with conducted EMI primarily. So we'll talk about that in detail, but literally this is stuff like capacitors and inductors and stuff like that, where you can make like a low pass filter, stuff like that. So it's very cheap, like I said, very cost effective. It doesn't really change your project a whole lot. The components are relatively small, and engineers are well acquainted with using these as solutions. So designs use them all throughout. Almost every design will use one, right? The next, moving on, is PCB layout. So this just has to do with where your components are placed relative to each other, if you have any quote unquote transmitters really close to receivers, you could just you could basically turn your entire PCB into like an EMI antenna, right? A giant EMI. You can amplify signals that you don't want to because of your PCB layout. Another smaller example is like an RCD snubber. So this is something we featured. I'm not sure if I've published this video at this point yet, but I think I've talked about RCD snubbers, but basically they're just another set of components like resistors, capacitors, diodes that you can put in order to dampen certain signals. And so these are just some, examples I thought offhand. There's probably a lot more, but these are ones that I use during, whenever I work as an engineer. So I just figured I'd mention some of these. So like I said, the key idea is to reduce your circuit's emissions in the first place and limit the amount of noise it produces. So we want to just limit how loud it is to begin with, not try to put a bunch of band-aids on something after the fact and try to deal with the noise after it's already making a bunch of noise. We just want to keep the volume low to begin with. So moving on to noise, right, there are two main types of noise when it comes to EMI noise being generated by your electronic circuit, your PCB. You have common mode noise and you have differential mode noise. So I just have like a little diagram I pulled. This is off like TI's website I pulled it off of. So I'll just kind of read this part of, there's like a presentation they had. You can, maybe I'll link it if I can find it. But basically with common mode noise, like I said, noise flows out in the same direction on both wires and returns via stray capacitance and chassis ground. So think about this as like your line, like you have positive and neutral, that type of thing. So you have your signal is traveling, down both wires in the same direction. That is what is known as common mode noise, and then it returns through, like I said, chassis ground or earth, which is gonna be that third prong. So you have like you have three-pronged outlets, right, that plug into the wall. That's what common mode, that's just the signal path that common mode noise takes. So mostly independent of load current, filtered with a common mode choke. So that's a type of component that we'll talk about in a second. So like here's the diagram. So you have source, which is, we'll talk about where the sources of this thing are in a minute. And then you have like the load, like I said, it travels through parasitic capacitance through to chassis ground. It's going to look like this. While compared to differential mode noise, like the signal noise flows out on one wire and returns on the other wire. So this is, like I said, this is more traditional looking circuits. I said you have positive to negative type of stuff. I mean, this is still positive to negative, but it's just a different negative, if that makes any sense. So it says it increases with load current, attenuated with a pi filter. So again, pi filter is a type of just a collection of a couple fundamental circuit components. And we'll actually get to them and explain them what they are right now. So now that we understand what differential and common mode noise are, we have to understand so we have differential mode noise, we have common mode noise. We got to mitigate both of them. And this little thing tells us exactly how we can do that. So here we are looking at, this is a piece of a circuit for what is a switch mode power supply. It's actually a flyback converter. I don't remember where I found it from, but all I did was I just took the part that shows the EMI filter. So I have it labeled here. So looking at common mode noise, it says filtered with a common mode choke. That's what this thing is right here. These things look like a little coupled inductor, right? So you have the little inductor looking humps and you have the two dots that show they're coupled. And then they have like their 4 pins. Let me see if I can find an example on Google and show you. So it looks like this thing, right? This little red thing. If you've seen any of these on a circuit board, that's a common mode choke right there. They're really big. They're usually at the base where the AC inlet part of the circuit is. If you have like an AC input, that's where you'll see a lot of these things right around there because they're filtering the noise and that goes onto the AC part of the signal. So you have CM choke. Another thing that filters common mode noise are going to be the Y capacitors. So you have Y capacitors. If you look, these go from, looking closely, so you have the 3 prongs, right? You have line, neutral, chassis, ground, or earth. So each of these capacitors goes from either line or neutral to chassis ground, right? So in this case, let's just call this one neutral and this one line. So you have line to chassis and you have neutral to chassis. And then here's chassis right here. Let me see if I can find a good example of, and these are, you can just search safety capacitor and you'll see what I'm talking about. Like these are good examples. They look kind of like little button things. And then here's another better example of something you'll see at the input. So like these little box looking, they're boxy looking things. They can be blue as well. I don't know if there's any blue, like right like this. All right, these are capacitors actually, right? And they're used to filter out noise. That's what a Y capacitor would look like as well. So moving on to another component in an EMI filter is the X capacitor. So this one goes between line and neutral. And again, it looks exactly like the picture I just showed, where it's the boxy looking component. And again, you'll see this right near the input of the AC right here. Let's see how this little, I mean, literally right where this J3 is. This is some type of inlet connector. And the X capacitor goes right there, right next to it. And so like the X cap, like I said, filters out differential mode noise. So it's one of those components. And then finally, if you look at differential mode, it says attenuated with a pi filter. So looking at this, right, this is what is known as a pi filter. It's just because on a schematic, it looks like, I mean, obviously we're looking at a schematic, so it looks like the Greek letter pi. That's why people made it that name. But it's just comprised of a couple capacitors and an inductor, and basically just form a low pass filter with this setup right here, right? And we can talk about we'll talk about how to design these in a later video. But you know, that's pretty much what we're working with in terms of some, you know, circuit level changes, some circuit design changes we can make in order to help mitigate EMI. This EMI input filter is one of those things. So I'll finish up with some closing remarks. So EMI problems usually revolve around switch mode power supplies. That's like I said, because that's where you have a lot of changing currents, a lot of changing magnetic fields, a lot of high currents and high voltages, right? So that's just where you have loud signals that are switching a lot. So that's where a huge like focus will be on whenever you're trying to handle EMI. Because anything that switches on and off fast, that's where your EMI problems come from. And like I said, because they involve rapid switching of high currents. So yeah, that'll pretty much do it for the EMI basics video. I'll definitely do some more videos on EMI stuff because it's extremely important as an electrical engineer that you know a lot. I mean, you know everything about EMI that you can, honestly, is design changes, test how you can test for it, all that stuff. So yeah, so if you like this video, go ahead, give it a like, please. That will really help out my channel. If you want to subscribe, I'll be posting videos just like this, you know, all the time. I think I post a video like every couple days or so, every 3 days. We'll be doing some EE projects. I already have one up that's completed on my channel. I'll be posting another one soon. If you have any ideas for projects you want me to do, just let me know. Pretty much anything you could think of that is electrical engineering, right? Any type of PCB design type stuff. Mostly I'm taking power supplies now. But yeah, so, you know, subscribe if you want to make sure you get notifications for whenever I post those. Yeah, that'll do it. So thank you so much if you made it this far. I really hope you learned something, and thanks.